In this video, we're going to discuss threads and concurrency. Why do we learn about threads? Because most modern applications are multi-threaded. Threads run within an application. Multiple tasks within the application be implemented by separate threads, including updating the display, fetching data, spell checking, answering a network request. They don't all have to run synchronously. Process creation is heavyweight, while thread creation is lightweight. So it lets you have multiple paths through code, but it doesn't require the whole rigmarole that comes with processes. It can simplify code and increase efficiency. I don't know if I agree that it can simplify code so much as just increase efficiency. Kernels are generally multi-threaded. So here's a multi-threaded server architecture. There's a request. The server catches the request and then creates a new thread to service the request while it goes back to listening. Some of the benefits are responsiveness. May allow continued execution if part of the process is blocked. This especially is important for UIs. It allows easier sharing of resources, and it's easier than shared memory or message passing because it's usually in the same process. Not usually, always. The economy is cheaper than process creation, thread switching, etc. And they are easier to scale. They allow a process to take better advantage of multi-processor architecture because, in theory, you could run each thread on a different processor if they're available. So let's look at some of the comparisons. Multi-core or multi-processor systems put pressure on programmers, and the challenges include dividing activities, balancing them, data splitting, data dependency, testing, and debugging. Parallelism implies a system can perform more than one task at the same time. Concurrency supports more than one task making progress. And it can be done using a single processor or a core, and scheduling, and to use to provide concurrency. So there are a couple different types of parallelism. There's data parallelism, distributes subsets of the same data across multiple cores, same operation on each. And there's task parallelism, it's distributing threads across cores, each thread performing a unique operation. Task parallelism is much more common. As the number of threads grows, so does the architectural support for threading. CPUs have both cores and hardware threads. Concurrency versus parallelism. Let's compare. In concurrent execution on a single core system, we've got task 1, task 2, task 3, task 4. We switch back to task 1, etc. In a multi-core system, we've got T1 and T2 running in parallel, T3 and T4 running in parallel. Again, T1 goes again, T2 goes again, and we get hopefully much better throughput. In a single-threaded process, boom, we've got one thread. In a multi-threaded process, we can have separate code, registers, and stacks, just like for processes, but much more lightweight, and each thread is running independently. A multi-threaded web server has a dispatcher thread, a web server process, and worker threads. And a dispatcher thread dispatches tasks to the appropriate worker threads. Amdahl's law identifies performance gains from adding additional cores to an application that has both serial and parallel components. Let's say S is our serial component or portion and we have N processing cores. So the speed up is less than or equal to 1 over S, the serial portion, plus 1 minus S over N. That is, if an application is 75% parallel and 25% serial, moving from 1 to 2 cores would result in a speed up of approximately 1.6. As N approaches infinity, speed ups approach 1 over S, basically fragmenting reducing the impact of the serial portion. Serial portion of an application has disappropriate effect on performance gained by adding additional cores. But does the law consider contemporary multi-core systems? It's a good question. It's more based on multiprocessors, but with multi-core, it's roughly the same. user threads and kernel threads. Typically, there are two types. User threads are done by user thread level library. Four widely used thread libraries are POSIX, Windows threads, Java threads, and Python threads. Microsoft has made considerable effort in making threaded programming easier in the .NET framework, to the point where some of it you don't even really have to think about. It'll just do it for you. Kernel threads, virtually all general purpose OSs include them, including Windows, Solaris, Linux, True64 Unix, and Mac OS. So, multi-threading models. There's many-to-one, one-to-one, and many-to-many. Many-to-one. Many user-level threads are mapped to a single kernel thread. One thread blocking causes them all to block. Multiple threads may not run in parallel on a multi-core system because only one may be in kernel at a time. Few systems currently use this model because it kind of kills some of the advantage of using threads. One-to-one, each user-level thread maps to a kernel-level thread. Creating a user-level thread creates a corresponding kernel-level thread and has more concurrency than many-to-one. The number of threads per process can be restricted due to overhead. Windows, Linux, and Solaris 9 and later all use this. Many-to-many. It allows many user-level threads to be mapped to many kernel threads. It allows the operating system to create a sufficient number of kernels. Solaris prior to version 9 used to allow it. Windows used to do it with threading fibers, but that is a concept that has fallen out of use and is no longer available. There's also a two-level model, except that it allows it's similar to many-to-many, but it allows a user thread to be bound to kernel threads. Okay, not very often used by modern operating systems. So they're different thread libraries. They provide programmers with an API for creating and managing threads. You can either use this library in the user space, or it could be a kernel level library supported by the OS. Okay, in Linux or POSIX standard, there is the idea of POSIX threads or P threads, and POSIX is a specification, not implementation. The API specifies the behavior, and implementation is up to the development of the library. Data abstraction and separation of behaviors is separation of concerns are used here. So here is an example of using P threads. We've got a function that the threads are going to call. We have a thread ID and a set of attributes. Here we say if we don't have enough parameters, we're going to blow out. So we're going to get the default attributes, create the thread, and by creating it, we start it, and then we're going to wait till it to exit and then rejoin the main thread. The thread will begin in this function, so when we pass in the runner and we start our thread, it will call it and run through this thread, and when it's done, we mark it as exiting, so you can say it properly exited. So the way we join 10 threads, join runs the thread is we create a bunch of worker threads, and then we use join to join them all together. They'll run in parallel. Windows, and this isn't really how you do it anymore. This is just the Windows raw API. This is kind of under the covers at like the operating system programming level. Our beginning is similar. We set up all our stuff, and then we create our thread, telling it to use the summation function. And if the thread handle is valid, we're going to wait around for it to finish when we close our handle, because we want to clean up after ourselves. Java threads are managed by the JVM, and they may be created by extending the thread class or implementing the runnable interface. In my opinion, interfaces are a great approach that aren't really emphasized in C++, and it's one of the advantages of C# and Java. For example, class sum would be our class, our base class, right? Or a basic class. Summation implements runnable, right? And so in summation, we take our parameters and set things up appropriately. And then when we run it, we just go ahead and sum up the values. And then we'll set the sum on sum value, the sum value class. So here's our driver, okay? We create a sum object, and we create a new thread containing a new summation object, and call start. And when we then join to run it, and when it is done, it will print out the results. So what's becoming more popular is what's called implicit threading. As the number of threads increase, program correctness becomes much more difficult with explicit threads. Creation and management of threads done by compilers and runtime libraries is much easier to use. A couple are thread pools, OpenMP, Grand Central Dispatch, and other methods include Microsoft threading building blocks. You just use, now there's the Microsoft threading library, which takes care of a lot of that, various thread pools, and there's the Java util concurrent package. A thread pool is a little different than threading. It creates a number of threads in a pool where they just wait. The advantages are it's slightly faster to service a request because we don't have to create it. And we can bind the number of threads in the pool, in the application, to the size of the pool. Separating the task to be performed from creating a task allows different strategies for running them. For example, tasks could be scheduled to run periodically. The Windows API supports thread pools, as do the .NET framework quite nicely. OpenMP is a set of compiler directives and an API for C, C++, and Fortran. I've never actually used this. Provides support for parallel programming in a shared memory environment. We create as many threads as we want by using the pragma parallel, and it runs the for loop in parallel. I think this is easy to make mistakes with, though. I don't think it's very clear or explicit. Grand Central Dispatch is for Macs, and it's an extension to C and C++, as well as it's used by Swift. It allows identification of parallel sections and manages most of the details of threading. Block is in with a up pointer. Printf I am a block will allow you to run those in parallel. The blocks are then placed in a dispatch queue and assigned to available threads in a thread pool when removed from the queue. There are two types of dispatch queues. Serial blocks are removed in first out order. It's called a main queue. And programmers can create additional serial queues. Concurrent, removed in FIFO order, but several may be removed at a time. There's 3 system-wide queues with low, high, default, and high priority. So we get a global queue, and then we dispatch onto the queue this method or this code. So let's talk about some threading issues and the semantics of fork and exec. Signal handling, which has both synchronous and asynchronous versions. How do we cancel a thread? We can either do it asynchronously or deferred. What are thread local storage concepts, and what are scheduler activations? Does fork duplicate only the calling thread or all threads? It depends on the version of Unix. Exec usually works as normal, replaces the running process, including all threads, something to be really aware of. Signals are used in Unix to notify a process that a particular event has occurred. A signal handler is used to process signals. Signal is generated by a particular event, and the signal is delivered to a process. Signal is handled by one of 2 handlers, either default or user-defined. Every signal has a default handler the kernel runs when handling signals. User-defined signals can override the default. For single-threaded signals delivered to a process instead of a thread. So where should a signal be delivered for multi-threaded? It delivers the signal to the thread to which the signal applies. And it delivers the thread to every thread in the process, or to certain threads. Or we can assign a certain thread to receive all signals. Okay, so there are different methodologies for it. Terminating a thread before it is finished is called thread cancellation. A thread to be canceled is called the target thread, and there are two general approaches. Async cancellation terminates the thread immediately, and defers cancellation allows the thread to periodically check if it should be canceled. Pthread, we'll look at some pthread code to cancel a thread. Here, we create our ID, and then we just tell it to cancel it. Thread cancellation. Invoking thread cancellation requests cancellation, but actual threads cancellation depends on the thread state. If a thread has cancellation disabled, you can't do it until the thread re-enables it. The default type is deferred cancellation. Cancellation only occurs when the thread reaches a cancellation point, and there's a method called test cancel, and then a cleanup handler is invoked. In Linux, thread cancellation is handled through signals. Now, there's also the concept of thread local storage, or TLS. This allows each thread to have its own copy of data. This is useful when you do not have a control over the thread creation process, for example, with a thread pool. It's different from local variables. Local variables are visible only during a single function invocation. Thread local storage is visible across functional invocations. It's similar to static data, but unlike static data, it's unique to each thread as opposed to the process. Each operating system tends to have different approaches to it. You may notice that on some of these topics we're going kind of light, and that's because these are more application oriented. Even though the threads may be maintained by the operating system, we're discussing them more in context of applications. Many Mendelian and two-level models require communication to maintain the appropriate number of kernel threads. Typically, it uses an intermediate data structure between user and kernel threads called a lightweight process. It appears to be a virtual processor in which the process can schedule user threads to run. Each lightweight process is attached to a kernel thread. And how many do we create? Well, that's a good question. It depends on the level of concurrency we're looking for. Scheduler activations provide upcalls, a communication mechanism from the kernel to the upcall handler in the thread library. This communication allows an application to maintain the correct number of kernel threads. So here's some operating system examples. In Windows threads, it's implemented all the way through to the current version. It implements the one-to-one mapping and kernel level threads. Each thread contains a thread ID, a register set, a separate user and kernel stack for when the thread runs in user and kernel mode, and private data storage area used by runtime libraries and dynamic link libraries. The register stacks and private storage are known as the context of the thread. It's kind of, you can think of it as like a thread control block, kind of like a process control block. The primary data structures of a thread include eThread, which is an executive thread block. It includes pointers to process to which the thread belongs, and to kthread and kernel space. Kthread is a kernel thread block. It handles scheduling and synchronization information, kernel mode stack, pointer to the thread execution block in kernel space, or thread environment block in kernel space. The thread environment block contains a thread ID, user mode stack, thread local storage in user space. So basically, we keep kind of thread control blocks all over the place. The eThread has a thread start address and a pointer to the parent process. The kthread has a scheduling and sync information as a kernel stack, and these are both in kernel space. And then finally, the thread identifier, the thread execution block is in user space. Linux calls them tasks instead of threads. I don't know why. Thread creation is done through clone. Clone allows a child task to share the address space of the parent process, and there are flags to control behavior. Some of the flags: clone fs is file information is shared, memory is shared, signal handlers are shared, and the set of open files are shared. task struct is what points to the various data structures. So this is your overview of threads, and it's pretty high level, but we're not going to delve too deeply in threads into this course, but we will see them pop up.